Hey guys, welcome back. We're going to move on to our next topic, which is special right triangles. We're going to have two different ones. One's an isosceles right triangle. The other is half of an equilateral. So we have a 45, 45, 90 and a 30, 60, 90. So that's what we're going to be learning the next 2 days. Before we do that, let's kind of really hone in on what we remember about the properties of isosceles triangles. So here I have three different types of isosceles triangles. They're isosceles because two sides are the same. And when two sides are the same, that means their opposite base angles are going to be the same as well. Whether it's an acute isosceles triangle, a isosceles right triangle, or an isosceles obtuse triangle, they're all going to have the same congruent base angles, in this case just depending on what our largest side is going to be. So we're going to hone in on this isosceles right triangle. So if we know this is 90 degrees, the base angles are congruent, then the other two remaining angles both have to be 45. And so we're going to call this a 45, 45, 90 right triangle because those are the angles. 45, 45, 90 is an isosceles right triangle. So if I have this isosceles right triangle, and it is a right angle, right triangle, then I know that the sides are going to be from the Pythagorean theorem. A squared plus b squared is going to be equal to the c squared. So let's find out what these sides, the ratio of the lengths of the sides, are going to be for the isosceles right. So to make this easy, let's let the legs be equal to 1 and then use the Pythagorean theorem to find the length of the hypotenuse. So when I plug this in, my two small sides are 1 and 1. So that's 1 squared plus 1 squared is going to be equal to x squared. Well, 1 squared is 1 times 1, which is just 1, right? So 1 plus 1 is going to be 2. So 2 is equal to x squared. All right. Then I don't want x squared, so I undo a square with the square root. So I'm going to take the 1/2 power of both sides, which is the same thing as a square root, and then I get the square root of 2. So x is equal to the square root of 2. So we have 1, 1, and then radical 2. And this is going to be the lengths of the ratio of the sides of a 45, 45, 90 right triangle. It's kind of like the most simplified, reduced ratio of those sides. But all 45, 45 isosceles right triangles are going to be similar and have proportional sides to 1, 1, radical 2. So we'll need to remember that. So if I start out with 1, 1, radical 2, that's kind of like our starting point or pre-image, and then want to multiply this by some scale factor. Let's say we multiply it by a scale factor of 2, then all the sides are going to be twice as big, right? So 1 is now going to turn into 2, 1 is also turning into 2, and then radical 2 is now going to be 2 times rad 2, which is 2 radical 2, right? Not radical 4, not just 4, but 2 times radical 2 is 2 radical 2. So our scale factor in this case is multiplying everything by times 2. So if we look at our extended proportions of 1, 1 radical 2, now it's 2, 2, 2 radical 2, which if you notice, that can be reduced by taking a 2 out and getting right back to where we started with 1, 1 radical 2. So notice they have the same extended ratio, the same proportions of the sides. It's just going to be proportional by some scale factor. And so all 45, 45, 90 right triangles are going to be some scale factor of 1, 1 radical 2. All right, so we can multiply it by 2, but if we multiply it by 2, we can also divide it by 2. So if I go backwards, I'm just going to go back the other direction here. So it's going to give me this little small triangle here. So instead of 1, now it's going to be 1/2 and 1/2, and then half of radical 2, which is rad 2 divided by 2. And that's already rationalized, so we're good. We could just leave it as that. Now, also, instead of dividing by 2 or multiplying by 2, we could really multiply it by anything, including multiplying it by 4. So here we have one here, still 45, 45, 90. 1 times 4 is going to be 4. 1 times 4 down here, still 4 as well. And then radical 2 times 4 is going to be 4 radical 2. So hopefully you're seeing the picture here. We can blow it up as much as we want, and there's infinitely many scale factors we can multiply it by that are greater than 1. That would be an enlargement. But there's also infinitely many, going all the way back to 0 back here, that we could, of proper fractions, that we could multiply it by or divide it by, however you want to look at it, that exists between 0 and what the original one is here. So let me show you a few more examples. We could also multiply everything by 3. So here would be the triangle, just 3 times as big. 1 times 3 would be 3. 1 times 3 is also 3. And then radical 2 is now 3 radical 2. Okay. We could also multiply it by a scale factor of 5. So that would give us this one here. Whoa, pretty big. So 1 times 5 is 5, and then 5. And as you probably guess, 5 radical 2. Okay, cool. So all these special right triangles are all going to be similar to each other, all the 45, 45, 90s. So if I show it in this way, we'd have 1, 1 radical 2. And if I have a side length of 2 and 2, this one should be 2 rad 2, right? But let's go ahead and use the Pythagorean theorem to show that that's actually true. So I've got two legs of 2, so 2 squared plus 2 squared is equal to x squared. That's going to be 2 squared is 4, so 4 plus 4 is going to give me 8. Then I end up taking the square root of both sides, right? So square root of 8 can be reduced. I'm going to break it down to 4 and 2, and then 2 and 2. And we're looking for any common pairs that can come out. In this case, we have, let me change my color real quick. We have two pairs of 2's, so a 2 can come out, and the 2 is left on the inside. Which leaves us with 2 radical 2, just as we expected, right? So we went from 1, 1 radical 2 to 2, 2, 2 radical 2. Just twice as big, right? All right, so what about 3, 3? 3 radical 3, right? So let's do the Pythagorean theorem. It's going to be 3 squared plus 3 squared is equal to x squared. 3 squared is 9, 9 and 9 is 18. So then we take the square root of both sides, right, which gives us radical 18. Can be broken down as 9 and 2. If you're noticing a pattern here, it's going to happen every time. 9 is going to be 3 times 3, and those can come out, right? So the 3's come out, and we're left with a 2 on the inside. So what do we have? 3 radical 2. So this length here is 3 radical 2. And if we do another one, 4, 4, 4 rad 2, 5, 5, 5 rad 2, 6, 6, 6 rad 2, whatever n times n, and then n rad 2, right? Okay, cool. So solving by similar triangles, if we are going from 1, so 1, 1 radical 2, and the leg is 1, and now the leg is 12. So what did I multiply 1 by to get it to 12? Well, I multiplied it by 12. So now all the other sides are going to be multiplied by 12 as well. So 1 times 12 down here would be another 12. And we know those two have to be the same. And then radical 2 times 12 would be 12 radical 2, right? So 12, 12, 12 rad 2, if you're noticing the pattern here. All right, now it can get a little bit harder because sometimes in this case we go from a radical to a regular number. So how do we do that? Well, good question. First of all, we identify we have the hypotenuse and the hypotenuse here. So the first thing is I want to draw my little scaled down model of 1, 1 rad 2 in the same orientation as the original one. Now on the assignment, I went ahead and drew them for you so that they're all in the right orientation, but we need to fill in 1, 1 radical 2. And if I'm going from the hypotenuse of radical 2 to a hypotenuse of 8, what do you multiply radical 2 by to get it from a radical 2 to a regular 8? Well, the first thing is I have to get rid of this radical. So I'm going to multiply it by a radical 2. So what is rad 2 times rad 2? Well, it's radical 4, which is really just 2, right? So if we square or multiply radical 2 by itself, it undoes the radical and gives us just regular 2. Now that we're up to regular 2, I still have to get up to 8. So what do I multiply regular 2 by to get it up to 8? Well, that's just 4, right? So 4 radical 2 would be our total scale factor. So 4 rad 2 times rad 2 is going to be 8. Now that I know my scale factor, I can multiply the 1's times 4 rad 2, which is going to be 4 rad 2. This one times 4 rad 2 is 4 rad 2 as well. So this is pretty much the hardest I could make the problems here is whenever we go from a radical to a regular number, just remember we multiply by the radical to get it to a regular number and then whatever is remaining. All right, so that was really fast, like 9 minutes. Awesome. So let's go ahead and get right into the assignment here. So number 1. First thing I want you to do is fill in the same orientation as our triangle here, the sides. It's 45, 45, 90, so it's going to be similar to 1, 1, and radical 2. And these two are indeed similar to each other, which means that they have some scale factor that exists between them. So we need to find out what that scale factor is. Let me go ahead and mark this just so you can see what's going on. So if I'm going from, the only side they give us over here is 20, and that's one of the legs, not the hypotenuse. So if I go from a leg of 1 to 20, what am I multiplying by? Well, clearly times 20. So what's the other leg going to turn into? Well, 1 times 20 is 20. What's the radical 2 going to turn into? Well, radical 2 times 20 is 20 radical 2. So we had two answers here for x and y, which is going to be 20 and 20 rad 2. Number 2, real simple on this one too. Again, fill in what we have here. Our small legs are going to be 1, 1, and then radical 2 is our hypotenuse. We're going from a hypotenuse of rad 2 to a hypotenuse of 24 radical 2. So how do I go from rad 2 to 24 rad 2? Well, you multiply it by, we already have the radicals, so the only thing we're adding to it, or multiplying, is 24, right? So times 24, so 1 times 24 is going to be 24. This 1 times 24 is also 24. So we have two answers on that one from the answer bank, which are both 24. Number 9. Again, orient it in the same orientation. We have a hypotenuse of rad 2 and then 1 and 1. The hypotenuse is now regular 10. So it would be easier to go from 1 to 10. I agree, but we're going from a hypotenuse to a hypotenuse, so you have to make sure you line them up first. So first question is, how do you get rid of the radical 2? How do you get to a regular number? Well, we multiply it by rad 2. So that's going to be a part of our scale factor. Now that we multiply it by rad 2, we still have to get it up to 10. So now that we're at regular 2, we multiply it by 5 to get it up to 10. So altogether, our scale factor is the radical 2 times 5, which is going to be 5 radical 2. So multiply the 1s times 5 rad 2, which will leave us with x is equal to 5 radical 2. All right, number 11. On this one, if you could print off the assignment, it'll be kind of cooler, but the one I'm going to post is going to already have the lines drawn for you. But if you want to measure it out with a ruler, as long as these are 1 centimeter, then your hypotenuse lengths should actually match the values over here, which is actually pretty cool. So this is something that's kind of more fun to do in class as an activity, but you can still get the idea. So if I have this length of 1 centimeter and 1 centimeter, this hypotenuse here is going to be a radical 2, which is a length of approximately 1.41. So I just put some approximations in there. So if I measure that length, it should be approximately 1.41. Yeah, just a little bit past 1.4, which is kind of cool. Then if I do 2 and 2, and then I connect that length here, that one should be about 2 rad 2, which is twice the last one, which is going to be about 2.83. And if I measure that, sure enough, about 2.8, and then a little bit past that. Cool. And then 3 and 3, so this one should be 3 rad 3, right? Which is approximately going to be 4.24. So 4.12, almost 4.3, but 4.24. Okay, looks good to me. And then 4 rad 2, which is roughly 3 or 5.66. 5.5, 5.6, almost 5.7. Yeah, so 5.66. Okay, and then 5, and 5 rad 2, which is approximately 7.07. So going up here. 7.07. I think I went a little bit far with the ruler. Okay, so it's actually going to be a little bit less than that. I think that one started out a little bit more. Okay, so there we go. Anyway, about 7.07. And the last one is 6 rad 6, which is approximately 8.5. And then when I measure that out, yeah, 8.5. Nice. So basically here, what we have is a bunch of similar triangles, 1 and then times 2, times 3, times 4, times 5, times 6, right? And you can see them all being scaled up together, which is kind of cool. Number 12, a square has a length of 11 radical 2 meters. So one of the side lengths is 11 radical 2, shown there. What's the length of the diagonal of the square? Well, if it's a square, it's got two 45, 45, 90 triangles, right? So if this is 11 radical 2, that means, see if I can duplicate that real quick, it means this is also 11 radical 2. So then the real question is, what is the length of x? So they're similar to 1 radical 2, and I drew them in the same orientation. So if I'm going from a leg of 1 to a leg of 11 rad 2, I'm multiplying by 11 radical 2. So what is radical 2? The hypotenuse times 11 radical 2. Okay, so rad 2 times 11 radical 2 is what we're trying to do. Well, you multiply, if you remember, from rules, and that's why we spent 2 days doing multiplication, simplifying these radicals. We multiply the parts in the radical, and then we multiply the parts on the outside of the radical. So 11 times 1, right, is going to be equal to 11, and then rad 2 times rad 2 is going to be a regular 2. So we have 11 times 2, which is equal to 22. All right. So this hypotenuse of rad 2 is now going to turn into 22. So that's going to be our diagonal. There we go. Number 16. Children climb 8 feet to get to the top of the slide. At the end of the slide is 1 foot above the ground, and the slide has an angle of elevation of 45 degrees. If the slide makes a straight line from the top to the bottom, how far does it travel down the slide? All right, so that's going to be the hypotenuse length. All right, well, if the total length is 8 feet, but it's 1 foot above the ground, we're going to subtract that 1 foot. The orange length here is actually going to be 7, if that makes sense. So it's going to be 1 less than how high the whole triangle is off the ground. So if I'm going from this leg of 1 to the leg of 7, I'm multiplying by 7. That's my scale factor. So this leg for x here is also going to be 7. And then the hypotenuse is going to be radical 2 times 7, which is 7 rad 2, right? So that would be the length of how far the child slides down the slide. 18. So we've got this little 45, 45, 90 here. I don't know if they told us, but we're going to assume that's a right angle because otherwise we can't solve it. So I don't have any measurements of this triangle, but over here I see this 11 rad 2. So that's going to be the same 11 rad 2, assuming that this is a rectangle. All right, so in the same orientation, I have 1 radical 2, and I'm going from a leg of 1 to 11 to a leg of 11 rad 2. So multiplying by a scale factor of 11 radical 2. So the other leg is going to be 11 rad 2 here, right? 11 rad 2, 11 rad 2. And then radical 2 times 11 radical 2. I think we just did one very similar to that, didn't we? So 11 radical 2 times radical 2. Well, rad 2 times rad 2 is regular 2, and regular 2 times 11 is equal to 22. All right. Anyway, that's my Taylor Swift impression. All right, so this is going to be 22. And the next thing we have is what's the length of B? Okay, well, if this is 8 radical 2, that means this part up here has to be 8 radical 2 as well. Let me go ahead and duplicate that. And then if we add those together, 8 rad 2 and 11 rad 2 are like terms because they're both radical 2. So if I have 8 radical 2s plus 11 more of them, how many radical 2s do I have altogether? Okay, well, that's going to be 19 radical 2. So we had 2 answers there, I think, for A and B. A question they like to ask is what's the perimeter? And so the perimeter, we'd add all these sides together at the very end. That'll be like a similar to a test question that you would have on this problem. All right, so less than 17 minutes, doing really well on time. I believe that's the last question I'm going to do. Oh, no. One more, I'm sorry. Number 19. So on this one, the question says that a very wise student, fellow student of yours, says that the perimeter of an isosceles right triangle will always be, it will never be a whole number. So it's always going to have some radical component to it. Do you agree with the statement? So if we look at our first one, which is the reduced ratio, extended ratio one of 1, 1, and radical 2, right? So if we look at that and we look for the perimeter, we add them all together, that's going to be 1 plus 1 is 2, and then radical 2 is just rad 2. We can't add those together. So we do have this radical component here, right? Oops, didn't mean to do that one. How about that? Okay, so we do have a radical component. So far he's right. Now, if I try to get rid of this radical, what would I have to multiply radical 2 by to get it to, let's say, regular 2? Well, we go from a radical to regular by squaring it or multiplying it by itself. So I'm going to multiply everything by radical 2, which is going to make this turn into a regular 2, which is great. So we got rid of that radical component. But when I multiply the other parts by this radical, 1 times rad 2 is now going to become rad 2, and this one, 1 times that's also going to be rad 2. So what ended up happening here, when I multiply by our scale factor, and multiply everything by scale factor, is now instead of having 1 radical length, now I have 2 radical lengths. And it's always going to be basically a trade-off between the two. So it's like whack-a-mole in Chuck E. Cheese or whatever. You hit one of them down and then 2 more pop up, right? You hit the 2 down, then the 1 pops up. So no matter what we do, we're always going to have a radical length, and our perimeter will never be a whole number. So this one in this case would be 2 plus 2 radical 2, because there were 2 of those that we could add together, which again is still going to have a radical component to it. It's never going to be a whole number. So yes, that was a very wise student. Or was it your teacher who told you about that? Or a worksheet that I got it off of. Anyway, it's a really cool discussion, and I hope you guys enjoyed that. Now, that one truly is the last problem I'm going to do with you. So if you have any questions, please let me know. We're doing our Snowmageddon distance learning and stuff like that. I will be live on Wednesdays from 11 o'clock on our Google Meets. If you need any private tutoring, I did private tutoring recently, and it took like 15 minutes to get some things clarified, and so I've got a lot of free time. Please hit me up, and we can always schedule time for private tutoring, and we can get you moving along with the confidence that you need. So I'll see you guys later. Can't wait to see you guys back in class, and things are hopefully going well for you. And I still miss having you guys in class. Enjoy the snow while we have it, except not the negative temperatures and stuff like that. But anyway, I'll see you guys later. Have a good one.